slides and then share with you a collab that we will use for this session. Okay, let's start. So, as mentioned earlier, I am going to talk to you today about deep feed-forward neural networks. So Timothy already presented me. Maybe something I want to add is that apart from my research interests, I'm also very keen on making AI fair and accessible to everybody. This led me to work with a deep learning in Indaba, which led me to be here with you today, for which I'm very thankful. So feed-forward neural networks or deep feed-forward neural networks are models where we have multiple neurons stacked into layers. These neurons are connected together in such a way that the information flows in only one way from an input layer to an output layer. That's why we call them feed-forward. We call these neural networks deep as soon as we have multiple layers in them, starting from 3 layers on. And in general, the neurons are endowed with a nonlinear function that we call activation function, which allows these models to encode a mapping or a function from the input space to the output space that is also nonlinear. So I like to start my presentations with Code's General, and today I'm inviting Jeffrey Hunton to tell us what he thinks about deep learning, and especially stressing out how deep learning is already making a lot of things behind the scenes much better. We can think, for example, of simple apps that we use every day to very specialized use like medical data analysis. And deep learning is already intervening in such applications, making them faster, more reliable, and in general better. So this is an important subject that we're talking about today. Just to situate deep learning in the AI landscapes. So AI in general is a collection of algorithms that can make what you call intelligent decisions. Such decisions are considered intelligent when they are not hard-coded, but learned in some way. Machine learning is inside that the field where we learn these decision rules from data. So generally we have a training data on which we train our models, and then we use this learning to infer new information on unseen data in the future. Inside machine learning, we find what you call representation learning. In this field, the data is progressively processed before making a decision and transformed into what we call features. And inside this particular field, we find deep learning. And in general, we call deep learning model a model that does this processing in a hierarchical way using multiple stages. Like, for example, as I showed an MLP or multi-layer perceptron, the model I showed you earlier. So deep learning is seen somehow or perceived in many cases as a black box, where we throw our data and somehow magically we have answers. So today I will try to demystify a bit of that, and particularly to show you some tools that we use to steer this data to start looking right, as it's said in the picture. To do that, our learning objectives today are the following. So first, we will see how to build a model using TensorFlow and Keras, and how to transform our large data set into a streaming pipeline that we can feed to our neural network architecture. We would like to understand how a model is trained and evaluated, and to understand the concept of in-sample and out-of-sample performance, and the concept of generalization, and how we can use different splits of the data to understand and deal with these issues. Also, hopefully, if the time allows, I would like to let you research and use some techniques that can be used to improve model generalization, and finally to think about some of the modern challenges that we face when we try to understand deep learning models. So I know this is a virtual session. It's not like an in-person tutorial, but I'm hoping that you can make this session yours. So I'm hoping or calling here for some interaction. So you have, I hope you have access to the chat at least, so you can ask questions, discuss. In many places in the Collab, you will see there is an invitation to think and discuss. I hope that you can be able to do that. That this way the session can be more interesting for all of us, I guess. So yeah, please feel free to stop me anytime and to ask any question you have, and in general to share your thoughts about the subject that we are going to talk about. So without further ado, I invite you to go to this link. This will give you a collab, and I invite you to make a copy of this collab in your drive. So I hope everybody has a Google account so you can use this collab. And then once you do that, I invite you to connect to an instance with the GPU and start reading. I will do this in the same time as you in a minute, so just we can do that together. So I will stop sharing my screen right now and move to the Collab. Was that clear for everybody so far? Or if you have any questions or comments on the presentation I gave already, please feel free to ask them on the chat.
Doctor, if you may share the link in the chat.
Yeah, sure, I will do that. I was going about to do it. Okay. Okay, I hope that everybody was able to arrive at this page. So as I said, please first go to file. Sorry, my Google is in French, but you will have save a copy in your drive. Do that. And then under Connect, I would like you to go to Manage Resources, modify the type of execution, and ask for a GPU as an accelerator. Share and then connect. Okay. Okay, I will start introducing this collab. Please stop me if anybody is having troubles connecting. So, all right, more precisely in this practical, we are going to implement and train a feedforward neural network. As I said, also known as the multi-layer perceptron that has multiple layers. So it's not very deep, but it has at least 3 layers, so we can start playing with depth. We will use a data set called fashion MNIST. So maybe, I don't know, maybe you are familiar with the MNIST data set. There is a data set of digits, handwritten digits. Fashion MNIST is similar in the sense that it has same size of images. It's also grayscale, but it has slightly more complicated images. So it's images of fashion items, of clothing. So here in this practical, again, we consider the practical issues around generalization. We'll understand this later on, and we'll try to introduce some important techniques in addressing that. For the data, we will get it from Keras, so you will see it later on as we progress in the collab. Okay, so the learning objectives, again, just to remind you, is to understand how to use TensorFlow and Keras to process the data into a stream, and also to build a network architecture. Sorry. I'm just having trouble removing the chat from here. Okay. So now, after that, we will see how to train and evaluate a model. Again, to explain the difference between in-sample and out-of-sample performance, and to understand generalization, and how to use a split of train, validation, and test to counter that. And finally, as I said, to think about some of the modern challenges in deep learning. Okay, so now the data. Again, the fashion amnesty is grayscale images. It's exactly 70,000 grayscale images divided into. I mean, it comes from the built-in function in Keras, as split into 60,000 images for training and 10,000 images for test. So the idea is to train a multi-layer perceptron to map each image to its class, and to be able to evaluate that on the test images, hoping that we can see good performance on the test images that we don't see during training. So this is an example of what you call a supervised learning problem. I think that you've learned the definition of such a problem earlier in this program. So that means that the data comes into images and targets that we will learn from them. And this is in contrast with other types of learning that you might either see or you will see later on in this program, which are unsupervised learning, where we don't have any targets, and reinforcement learning, where we have an agent that learns to maximize the reward rather than having input images and targets. So this is the function that you see here is what we use to load the data. This is a built-in function in Keras, so the data is already prepared for you. If you run that, you'll have it split into train and validation and test images. The text labels you see here is just to get a practical sense of what this data does. So why now, further than this split into train and test, we will split our training set again into training set and validation set. And why we do that? So in general, our models come with many hyperparameters that will affect the final performance of the test of the model. So our goal is to make our models performant on data that we don't see during training set. The test set is somehow a proxy for that, for this future data. But of course, we can't train on the test set. That would be considered as cheating. But to be able to tune our models properly, to choose properly our hyperparameters, what we can do is that we can take part of the training set and use it as a validation set. So this is what we are going to do here. So this train and validation set, we split it further into a training set of 50,000 images and a validation set of 10,000 images. So now I would like you to get familiarized with what the data look like before we start. So this data, as I said, is composed of 28 by 28 matrix of grayscale, the same size of MNIST. And it is data of clothing or fashion items. So you've seen the text labels. You can have, for example, the numerical label one is associated to the text description trouser. So if you run the two cells below, you will see multiple input data. So I'd like you to run the Collab up to here and particularly to run this cell I see here for where we are showing 25 randomly selected images. I would like you to run it multiple times and take a look at the data. I'll give you a few minutes to do that, and I want you to think about how the data look like, what might be difficult for a classifier to distinguish here, and why that would be difficult. So I don't know if the participants are able to speak. If so, please raise the hand and we can allow you. Otherwise, please use the chat to discuss or to put anything that you have in mind concerning this data. Or if you have any questions as well, please feel free. So let's take, say, 2 to 3 minutes to do that. And as soon as I have a few thoughts, we can move forward. So first, was everybody able to connect the Collab to GPU and to start running things? If not, please let us know. Okay, great.
All right, looks like we have a hand here. Samuel, if you may speak.
Yes, hello.
Yes, please.
Yeah, I'd like to repeat how to connect it to a GPU because I tried running it and it was not running. I think I missed a point on the connection.
All right.
Thank you for speaking up, Samuel. So again, if you do you see my cursor, my mouse moving on the screen?
Yes, please.
Okay, so here on the top right, you have connect. So you can, again, sorry, this is in French, but you'll have manage resources or something like that in your options. If you go here, you can see, modify the type of runtime. You'll have a choice on the accelerator that you want to use, and I'd like you to choose GPU. Then save and click on connect. Let us know if this works. So were you able to connect?
We have another hand.
Yeah.
Yes, Patrick.
Yeah, I'm just confirming that I'm able to connect.
Okay.
But it's not from the version in my drive, but the other version that was okay in the Collab. So when you try to do it from the one in the drive, that's where you get challenges, I think.
Okay, so if you're able to connect in any way, that works for me. I mean, I guess you won't only be able to modify things on that. That's a bit of a shame, but yeah. Okay.
Yeah, actually, I've tried again and it works on both, actually.
Perfect. Thank you for that. Yeah.
Welcome. Thanks.
Yeah.
There's also one from Simon Peter who says they can only view resources and not manage resources.
Okay, can you are you able to choose GPU? Actually, I'm guessing even if you can't connect to a GPU is not a problem. You'll be able to run the Collab. It's only a matter of speed. So if you are able to connect to any type of runtime, please go ahead and do it. So at least we can work with the Collab.
We also have one from Millicent.
Yeah.
Millicent, please talk to us.
Hello, Timothy.
Yes,
I was
please.
just providing alternative way of changing it than that one that doctor just gave us. If you want to change and your Collab is in English version, just go to Runtime. There is up there is a Runtime place. Then you click on Runtime. You just say change Runtime type to GPU. It is very easy.
Thank you for that piece of information. We also have Paul who wants to say something. Paul, please.
Yes, thank you. When I run, I get error. I still get error. I don't know why.
Can you tell us what error do you get?
Okay. The error says that error name error. We use the matplotlib library plotting library to visualize. That's what it's giving me.
Can you please copy paste the error that you see on the chat, please?
Okay. Okay.
Okay, so while I think just to move forward, while I'm waiting for Paul to send me the error, I will just do what I ask you to do here on the screen, and I will ask you to again think of what these data challenges are, what can be hard to classify, and why you think is that, and just give me a few thoughts on that, please. So I'm running this again. So you see it's a bunch of shoes, dresses, coats, pullovers, bags. And another time. So by looking at these images, can you think of what can be hard to distinguish, for example, and why? For example, can you think of two classes that are similar or hard to classify? Yeah, the coat and shirt. That's one. Exactly. Can you elaborate a little bit more? Why is that hard to distinguish? That's correct as well, coat and dress. Yeah, so the similarities in color is one thing, but everything is similar in color here. Everything is in grayscale. So I think here the challenge comes more from the features, what you call features of the images. So a coat and a dress, for example, can both be with sleeves with similar length. So those are features that are common, making them hard to distinguish. Same for coat and shirt, for example. They can come both with buttons. They can have the same color, for example. So it's yeah, it's they have similarities in the features that we use to classify them, even as humans, and it is very likely that the machine will face the same issues. Okay. So now that we've seen this data, let me talk about how to prepare it for training a deep model on it. So again, as I said, we have now the images stored in a very large tensor of a shape of 50,000 times 28 times 28. And the labels are stored in a 1D vector of shape 50,000. So to train a model, we want to use what we call a mini batch stochastic gradient descent. I don't know if you're familiar with gradient descent in general, but we have a bit more explanation in the bottom of the Collab, so we'll come back to that. But in general, what we want to do here is to store our data into what you call small mini batches. Those are smaller sets of images. So rather than 50,000, we want to have them into, for example, 128 images at once. Those batches should be random, so not coming always in the same order. We would also like not to have images of all from the same class in one batch. And those are questions that we are going to think of a bit later, hopefully if we have time. So what we need to do is to shuffle the data and split it into smaller sets. Also, the data comes into NumPy arrays, and we want to transform it into TensorFlow tensors. So maybe just a few words on the differences. Those two data structures are very similar. So you can see tensors of TensorFlow as somehow a multi-dimensional factor or generalization of these arrays. The particularity of TensorFlow tensors is that they are more suitable to acceleration through GPUs, and they are immutable contrarily to NumPy arrays, meaning that you cannot change values manually into these tensors. So in order to do these operations, this batching and shuffling, we will use the TensorFlow dataset API. It comes with multiple reusable components and functions that we can use to build our data into a stream that will be served to the network later as we ask for them. So this will allow us later to especially to work on large data sets. So as we said, we've seen here, this data set has 50,000 images, but if you think of more modern data sets that we use in computer vision, like ImageNet, for example, we're talking about millions of images. So we really need to do this batching for this type of images. It's not only a matter of algorithmic decoration or something, it's really a need. Also, it has using this stochastic gradient descent and batched stochastic gradient descent has an effect on the performance and generalization. And again, you will discuss that a bit later. So first of all, we start by defining the batch size. This is a hyperparameter to the model. It will have different effects. It will affect the speed of conversions. It will affect the memory that you use, but also it will interact with what you call the learning rate used in gradient descent. Again, this is a point that we will discuss later. So for now, let us just see how we build these data sets, and we'll think about these components a bit later together. The first thing, as we said, to do is to change the NumPy arrays into tensor, and as you see here, this function does that for you from the TensorFlow dataset API. Then we are able to pre-process the data in any way that we like. So here I'm doing a simple operation for numerical stability. I will divide the inputs by 255 and cast them to be float rather than ints. This is what I do here with this mapping function. So lambda is just an anonymous function. I'm not sure you're familiar with that, but you can replace that by any defined function. You can define a function separately and call it into map, and you can apply any function you would like to your data set this way. After doing that, we shuffle the data. So this is the shuffle function again coming from the dataset API. So as you see, we provide a buffer size. So an example is to use 10 times the batch size. So this way, the algorithm will load 10 times the batch size of your data to pre-process in your pipeline, and then serve to the model one batch size at a time when it has enough, and when the model asks for it. And so this buffer size can affect your memory usage. So we would like it to be quite large to do pre-processing in chunks ahead of time, but not too big as to exhaust your memory resources. So I guess as a guideline, 10 times the batch size is pretty classic, and it's a good way to start. Again, and finally, we chunk the data into batches. So now here we have the training set into batches of 128. So now we do the same for the validation set, same operations, basically converting into slices and casting the values to lie between 0 and 1. So, so don't worry about this now. We will speak again about validation later. So this is a part that you might modify a bit later. So yeah, this is the data. Let me know if this is clear or if you have any questions about what we did so far. Okay, if no questions, let us move forward. I'm hoping that we can see some of the interesting features for the training in the later cells. So, okay, so now the model. Again, we are using what is called a feedforward neural network. So I remember this image that I showed you in the presentation, this multi-layer neural network. A feedforward neural network of n layer can be defined by this recurrent call of function. So the input would be f0, and then each layer will modify the previous layer by first applying a linear projection, and then applying a non-linearity that we call activation function. So before this question that you see here, I have another question for you. So the fact that this function is called recursively this way, or this built on into layers of the network, that gives us a very useful tool to train neural networks that we call backpropagation. This definition allows us to apply a very simple chain rule to compute the gradients from one layer to another. And I want you to take a minute to think of the challenges that this might impose. So think, for example, again, a chain rule would multiply the gradients coming from the later layers by the ones coming from intermediary layers, and it goes this way from the last layer to the first layer. So for example, if we have a very small gradient in the output layer, what would happen inside the network, given that you have multiple layers and multiple multiplications like that? Any ideas? Okay, so one of the challenges that come from using depth, okay, I'm going to repeat. As I said, the network defined this way allows us to do backpropagation from last layer to earlier to the first layer. And we use a chain rule to do that. So this way we multiply the gradients coming from the layers closer to the output by the ones from intermediary layer as we go backward in the network. So the question was, what happens if we have small gradients coming from the outward layer, the output layer? So what I wanted to make you think of is one phenomena that we observe due to depth, which is called vanishing gradients. So what can happen is, because of this multiple multiplications, if we have small gradients that we multiply together, these gradients will grow smaller and smaller as we go backward in the network and potentially vanish. When a gradient vanish means that we don't have any learning signal in the network. So we can't learn anything anymore from the network, from the data. This is a situation that is challenging because that can mean that the network is stuck and can't progress into learning. And the counterpart to it is when we have a large gradients, then when we multiply it progressively by intermediary layers, we can obtain what we call exploding gradients. And this will mean that your learning will effectively diverge and not converge anymore. So those are challenges that we can face due to depth, and we have multiple techniques to counter those. One of them is the use of particular activation functions. That leads us to the question here. So why do you think we need nonlinear activation function? More particularly, what would happen if those activation were linear? If sigma I here would be just a linear function, or just the simplest case would be an identity activation function, what would the network encode effectively? So if you look at these functions here, again, let's think of sigma I being just identity. So if x is first just multiplied by w1 and added to it by b1, and then f1, which is in this case just a linear transformation of x, is also multiplied by another matrix and added to a vector, and progressively, what would be the kind of mapping from x to the output here? So this means that we are just doing multiple linear operations one after the other, or composing linear modifications or applications. What would be the kind of mapping from the input to the output in this case? Okay, so the answer is, in this case, if sigma I was nonlinear, then the whole network would encode a linear function in the end. So just composing linear functions together will also be a linear function. This means that having these multiple layers together won't really have an impact on the kind of function that we encode. It won't increase the complexity of the function that we want to encode, and it will only be able to model linear dependencies between inputs and outputs. So the data that we have here is more complicated. It should be dealt with nonlinear function. So we do need these nonlinearities. So you have here a bit of reading on the nonlinearities, but I'm aware of the time, so I just give you the gist of it. So remember the problem of vanishing gradients we mentioned earlier. So one way to deal with that is to use a particular type of activation function. So one popular activation function that is used recently is called rectified linear unit, or ReLU for short. So the ReLU function is simply 0 for negative values and a linear function for positive values. So it will be with a kind of a change of slope in between. This activation function is popular because it actually deals with the problem of vanishing gradients, because it doesn't have a saturation for it, because I mean, just as earlier on, we used to have neural networks with what you call sigmoid functions, or the S function, that is, it goes from 0 to 1 and saturates at 0, saturates at 1. So for most of the time, the gradient from this function is close to 0. It only has signal in between, in the transition between the two parts, and which is a very small portion of your space, and it effectively led to vanishing gradients because of this this property of its gradients. So the ReLU, because it doesn't saturate, it doesn't have this saturation, suffers way less from vanishing gradients. This is one reason why it's popular. The other activation functions can be seen in other models, like the recurrent neural networks that you will see in coming days, for example. I'm thinking particularly about the 10H function and the sigmoid function. The softmax function is usually used as in the output layer to transform your outputs of the network into class probabilities that we can use for classification. Okay, so now let us build this model and configure it. So here I'm going to use the Keras layers, and more particularly the sequential component of it, to stack layers together. So again, I'm just going to show you a way to use what you called a fully connected feedforward neural network. Later today, I think you will see another type of networks called convolutional neural networks that can be more suitable for images. But here I'm limiting myself to fully connected neural network. So the first layer is just to flatten the input. So we have 28 by 28 matrices as input. So the first thing is to put them into a vector to be able to apply fully connected the neural network afterwards. Then I'm having three layers afterwards, going from 784, which is 28 by 28, to 2056. Then from 256, then from 256 to 128, and then from 128 to 10, which is the number of classes that we have here. So let me run the cells that we have. just to say again to define our model, and just if we want to restart training at any time, you need to rerun this cell, because otherwise the variables of your TensorFlow model won't be reinitialized, and you will be effectively just doing more training on the same model. So it's important to rerun this cell every time you want to restart training. So let us take a look at the model summary. So this is the number of parameters we have, some over 200,000 parameters in just 3-layer network. And yeah, I'll let you think later on this question. Just want to move forward to show you more interesting things. So before training the network, we need to define something more. We need to define what you call the loss. So we have a question from Oken saying that, do activation function map to higher dimensions? So activation function can have multiple definitions. So you have, for example, if you think of what you call pooling function, it maps to lower, not higher dimension. So it can change the dimension, but as it's defined here, it's actually just one-to-one mapping, and so just one dimension to one dimension, and it's applied to entry element-wise to the vector of your input from the physics layer. This is the activation function that we're seeing here. For the pooling function, I think you'll see the definition of that for that later on when you learn about convolutional layer. So link on the notes that being explained. So you have the Collab, hopefully. Someone asked to the link for the notes being explained. So the notes are basically in the Collab. I'm detailing a bit more, but you have links to read more on the Collab if you are interested. I will try to detail this a bit more later in the solution Collab that I will share with you later on, if I have time for it. So I don't promise 100% I do it, but I will try my best to do it, to give you some more explanations on the solution Collab later on. So just the loss is a way to measure how far we are from the target, which is learning to map the inputs to the outputs that we have in our training data set. And so after that, the loss would be differentiated and back propagated to the network to adjust our weights to much better the mapping between the inputs and the outputs. So here we are in a multi-class classification setting, and the classical choice for this setting is the cross entropy loss, also known as a negative log likelihood. So for this loss is defined as following. So if you have a probability output from your network, so the vector of probabilities, again, we use the softmax function to map any logits, or what you call logits, any output or real valued output into probabilities. So summing to 1 and having values between 0 and 1. And you also have what we called a one-hot encoding of your class. So this is an indicator vector where you have 1 at the position of your true class and 0 otherwise. And the cross entropy loss is defined by the following expression. So if you notice, the indicator function serves to take in only the log probability of the true class, and if we minimize that, then the lower loss will correspond to the probability being close to 1 for the true classes. And yeah, and the better the model will be performing. Sorry. So we don't need to write the function ourselves. Again, I will let you think of these questions later on. But because of numerical stability, we will use this function from Keras. It's called sparse categorical cross entropy. This is the most classical choice. But for this function, so we won't need the one-hot encoding. It takes the integer labels. It also takes the unnormalized logits. So we don't need the softmax function. It is already encoded in the loss function. And again, so you have here the classical definition of cross entropy. You can understand it from here, but this function is just doing all these steps for you, and it's more numerically more stable. That's why we choose that. If you have labels in some datasets that are provided in one hot format, you can use the categorical cross entropy loss instead of the sparse categorical cross entropy loss. You can refer to the TensorFlow notes to have more details on these losses. But also just another note is that when you don't have exact labels, but rather distributions on the labels, like for example, you have humans labeling your data, and the human will give an answer not just for the class, but also with a degree of confidence. So the labels would come into a form of probability as well, probability vector. Then you can still use the cross entropy loss by changing the one hot label by this probability vector. Okay, so now we are ready to train our model. So to do that, we go through our data, the batch data, using stochastic gradient descent, and we do this in what we call multiple epochs. So we go through our data iteratively by going through the whole data sets in one epoch and then repeating it. So first, what we do is we get the predictions of the model on the current batch of training images. Then we compute the average of the loss on the batch that we've seen by, again, measuring how close we are to the true targets. After that, we compute the gradients of the average loss on this batch, and this gradient will tell us which direction we should go move in the parameter space in order to make our loss smaller. And finally, we adjust the parameters of our network by taking a small step in the direction of each component of the gradient. And we have a learning rate that controls the size. So during training, we want to track some metrics to see how our classifier is performing, and to do that, we will track the loss and what you call the accuracy, which is measuring the portion of correctly classified samples in your data. So I'll let you read the difference between computing gradients in earlier on TensorFlow, what you call computation in graph mode, and the eager mode that is more in the more recent versions of TensorFlow later on. So this is just technical differences, but we will see how to do it in TensorFlow too. So in eager mode here. So first of all, for training, we need an optimizer. So here we are going to use an optimizer that has been shown to be successful in many cases. It is called Adam. So Adam doesn't do only gradient descent in the classical sense. It's a second order gradient descent. So it takes into account some second order information on your gradients, and it helps to adjust the learning rate in a way to make the learning more efficient. So after that, we need the loss object, that is the sparse categorical cross entropy that we just mentioned, and we need the metrics that we mentioned earlier, so the training loss and the training accuracy that we are going to monitor. So we define a number of epochs, so a number of times we'll go through our data set. Here we use 50, but you can increase or decrease that as you play with the code. And we would need empty lists to track loss and accuracy for every epoch. So the function you have here is what we use for training. So first thing is to compute the logits and then the loss. Again, the logits is just the unnormalized scores outputs of your network. And we do that inside what you call a gradient tape. So if you have read the text on the gradient computation, you'll see that in eager mode, we need this gradient tape to be able to store the order in which the operations are performed from the input to the output to be able to compute gradients backwards later on. So then we compute the gradients and we apply the gradients using the optimizer that we defined here. And then we add the current batch to the tracker of the metrics that we defined earlier. So where you see a to do here is where you are going to fill in the validation function, and afterwards we run into epochs, as I said, and loop into the data pipeline inside each epoch by doing for each batch applying this training step that we just defined, and then we can track the train loss and the train accuracy while we progress. The
Looks like we have lost Dr. Amal, but I have a feeling she's going to get back to us shortly. In the meantime, we do have some questions. All right, she's back.
Sorry, I lost my connection. Do you hear me again?
Yes.
Okay, great. Sorry for this interruption. So let me share my screen again. So as you see here, my code was running while I was interrupted, and you can see the accuracy on the training set progressing as we train. Okay, so now if we plot the loss and accuracy versus epochs, we see how the loss is decreasing while train and the accuracy increasing. So let us now visualize some of the predictions of the training on the training set of our model. So I don't know if we see wrong. So on this batch, everything seems to be correct. If we run it again. Yeah, so if you see here, you have an error where the model actually predicted a shirt for a t-shirt or a top. So again, we see the difficulties of distinguishing between classes that we mentioned earlier when we started discovering the data set. Okay, so let us now test our model. So we have obtained in the end around a bit over 0.1 for loss and more than 90% accuracy. So that is pretty good already for the training set. So let us see how this will behave on unseen data. So this is why we call it out of sample performance now. So this performance 90% is in sample, is in on the training set that we seen during training and with which we adjusted our parameters. So now the problem is if training loss is very low, that's as undesirable. And I hope I'll have the time to say to precise why I said can be considered here. So the problem is when we push this loss to be close to 0 on the data set, on the training data set, that means it not only fit the true signal that we are interested in, but also can fit the noise that comes with the data. In this case, if the model is really has learned to adjust the noise, it can perform badly on unseen data or out of sample. But to be able to assess that properly, we test our model on held out test data. Again, never, ever, ever train on the test data and never adjust your model on the test data because that would be cheating. So the idea is to try to really evaluate our model on the test data only at the end of our training as little as possible to be the closest possible to this out of sample performance. So first we will again convert our data to tensors and project and map it to 0, 1 as we did for the training and validation data. And then we test on our data. So here you see the loss is much higher than the training loss and the accuracy is significantly lower. So we had like 94% on the training data. On the test accuracy, on the test data, we have only 88%. And if we try to see some, so this seems correct. This also seems correct, but I guess if we continue to, we have pullover and coat here, we have t-shirt and shirt here. So yeah, we have some errors here. Again, with the same classes that we mentioned earlier. Okay, so this difference between the training and test set is what we can call overfitting. So the data, the model fails to generalize from in-sample performance to data that it hasn't seen during training or out of sample. So again, there are ways to address that. I'm hoping that to have time to at least mention a few of them. I guess, unfortunately, because of time, we won't have time to code things yourself, so there to research them, but I invite you to do so later. I guess it's important that you read things by yourselves to be able to get familiar, but I present some of them quite quickly in the remaining 20 minutes. Just a question, again, just to make sure that you are aware of that, why we should limit the number of evaluation on the test set. This is really an important point. What happens if we evaluate again and again on the test set? What can happen? just to hypertune, to tune our models and our hyperparameters by evaluating multiple times on the test set. What can happen then? Exactly, it may lead to overfitting on the test set. So if we tune your hyperparameters on the test set, then again, the model can be overfitting to this test set, and it won't be a good proxy for unseen data anymore. So when your model is really faced with real world unseen data, it won't behave according to the predicted way anymore. So in order to avoid that, what we can do is to use validation. So again, this is where we use the validation set that we held out from the training set earlier on. So rather than evaluating multiple times on the test set, we can again approximate this test set by a held out set from the training set. So this validation set can be used and reused during training to select hyperparameters, to select, for example, the batch size, the learning rate, to modify the network architecture. And once we are happy with the performance on the validation set, then we can apply our model to the test and see how it behaves. But yeah, so the validation set again will act as a surrogate for the test set here. So, well, the first task I wanted you to do is to implement the validation step into your code. So this will be very close to the test set. So again, unfortunately, I will let you do that in your own time later on, and I will send you by the end my email address, and I'd be happy to take any questions after the session. I guess 1 hour and a half was shorter than what I expected. But yeah, so when we do this validation, you'll see that effectively the loss on your validation, the accuracy of your validation will be very close to your test set performance. So when you play with the model, you can test on the validation set, adjust your hyperparameters before moving to the test. Okay, so now when we see this generalization gap, what can we do? There are multiple techniques to deal with that. Most of them are called regularization. So the global idea behind regularization is to somehow limit the complexity of your model and limit your search space to a smaller search space, hoping that it will be more regular and therefore being able to generalize better to unseen data. So the first most classical way to regularize your model is to apply what we call L1 or L2 regularization on the weights. So this is something that we inherited from linear model literature. The difference here, which is in my mind crucial, is that for the case of linear models, the weight vector effectively defines the function that you encode. This is not the case for neural networks. However, it's a simple enough regularization. It does limit your network in some way. It just doesn't have a link to the function that the network encodes as much as for linear models. So having such regularization is important. Okay, but in a limited way. Maybe again, just let us take a look at the documentation together. So the Keras API comes with the definition of the regularizer into the layer, so you can add a kernel regularizer for the weight vector and the bias regularizer for the bias, and you can choose between L1, L2, and L1, L2 with a penalty. So what does this do? Effectively, this will add to your objective function some constant times the L1 or L2 norm of the weights of the layer, or also a combination of L1 and L2 norm. Is that clear to everybody or not? So again, maybe let me show you where to do that. If you go back to your the definition of your model, to apply L1 and L2 regularizer, you can add here into the dense layer, you can add kernel regularizer, bias regularizer, and choose between L1 and L2 with the defined alpha, or with the defined penalty constant. This penalty constant is a hyperparameter. So again, we use a validation set to tune that. So let us think what these regularization do effectively. If we think of the L2 regularizer, for example, so any idea what this does? If we add to our objective a constant times the L2 function, the L2 norm of the weights of the network, what happens to the weights of the network while we train with this objective? So what happens here is that the weights of the network will stay small, especially if we initialize them to small enough value. The weights of the whole network will stay small. So effectively, constraining the network to a certain function class, let's say. The L1 regularizer will have a slightly different effect. The L1 regularizer will enforce what you call sparsity. So this regularizer will push as many weights as enforced by the penalty constant to 0. And it will sparsify the model this way. So this is for the L1 regularizer. Another way to improve the model generalization is to operate what we call dropout. So you have in the Collab a link to the documentation of TensorFlow and to the research paper of dropout. Just a few words on dropout. So dropout, again, it can, if you look at the documentation, the Keras allows us to just add a layer to the network. So again, if you go back to the model definition, sorry. If we go back to the model definition, then to apply dropout, we can add layers after each dense layer as defined here. So using this Keras layer. So dropout comes with a hyperparameter called the rate, and this defines the portion of your layer that we are going to drop at each iteration. So this is how dropout operates. At each iteration of your training, dropout will just remove a portion of the connections, or of the activation, sorry, therefore operating what we call a model averaging. So artificially, by using dropout, rather than only having one model that is the fully connected model, you have a family of sparser but much more models that you can learn from. And doing this way, we artificially sum or average the performance over these models. And this is a way also to regularize the training. Another way that is that came into literature more recently is what you call batch normalization. This is also a regularization method, and it was created for multiple reasons. So the main reason, or the main reason that is stated in the research paper about batch normalization, is that because we are using random batches, the mean and variance of your intermediary layer change during training, effectively making the fitting of your deep model to your data more complex. And what batch normalization do, it's to counter this phenomenon that you call covariate shift. It also helps with vanishing gradients and allow for much larger learning rates because of that. So this is the reason that was stated in the research paper, but this has been questioned a lot in the recent literature. So I'll let you read about batch normalization and the discussion that came after it. But maybe one of the more recent view on batch normalization and what it does is that it actually effectively corrects the initialization of your network. And maybe by cleverly initializing your network, you can alleviate the need for batch normalization. So yeah, this is a quite advanced subject, so I'll let you read in your own time about that. But the way that batch normalization does is that it stores the parameters of on the mean and variance of your intermediary layer during training, and then use those parameters to correct this covariate shift during inference. Okay, so another way to deal with generalization is by artificially increasing the size of the training data. Again, overfitting happens, especially when your network is too complex compared to your data, in a way that it fits the noise as much as the signal, the input signal, the true input signal that we are interested in. So sorry, I'll answer the questions on the chat in a few minutes. Okay, so the other technique that we can use is data augmentation. This way we artificially augment our data to make it match the complexity of the model. So we can do multiple operations on the data to augment it, like, for example, mirroring it, flipping it horizontally or vertically, cropping it randomly. So rather than having the full image, we have multiple crops in many places, rotating it differently, randomly. But so here in this particular data, maybe the one thing that we can think is useful is to flip it horizontally because of the structure of the data. Here, all the data is centered in the center. All of them are in the same direction. So it's rotating it, for example, will make it much more complex than the test data that you'll see at test time. So we can, for example, flip it horizontally to augment our data here. But the operations I mentioned are useful for natural images. For example, for a data set like ImageNet, where you have objects in multiple places in the image. So crops are useful. The image can come in different orientations, so rotation is also useful. And this way you can augment your data without moving too much from your test set. Okay. Let me ask some of the questions that are in the chat. So the first question is on the difference between L1 and L2 regularization. I think I mentioned a bit on that. So again, L2 regularization will force your weights generally to be small, close to zero. L1 regularization will enforce sparsity. So rather than having just generally small values, it will enforce some of your values to be zero. The second question is on dropout. So the question is about the seed in the dropout. So the seed is just to initialize your random number generator in general, and many of randomness components in models in deep learning in general will come with a seed. The importance of this seed is for reproducibility of results. So if you want to see exactly the same outputs, you need to specify seeds for your random number generators. And it is important also because, I mean, to report behavior properly, the best way to do is to average multiple runs on your validation set to see how the model is expected to behave in unseen situations. The way to enforce that is to test with multiple seeds and average afterwards. Okay, so highlights on Keras and TensorFlow. So Keras and TensorFlow are not competing things, they work together. So TensorFlow is came first, actually. It's basically what Keras runs on, and Keras is an API to make things easier for us. Keras is just an additional layer on TensorFlow to define layers of your network, for example, or operation for augmentation or multiple things to make things easier for us to define models. And the other question is, what is the importance of having testing data? So again, testing data is what will approximate the expected performance of your model on unseen data in the nature. So the validation data, again, is used to tune your models, to choose these hyperparameters. And later on, if you want to approximate how your data behaves on data that you haven't seen before, you need a test data that is different from the validation data. Okay, so someone also asked on more light on dense layers. Could you please, Yasin, specify your question?